The presentation is visible to everyone.
Yes, sir.
It's fine. So today is lecture number 22 of this advanced concept in steel technology, and today's topic is basically on this secondary steel making process. I am sure that you people have well knowledge on this primary steel making process, secondary steel making processes, right? And since you remember, in the previous lecture we have talked about something about that quality of steel, okay? Because if you remember, three things are very important for an industrialist. One is the quality, because if quality will be poor, then customer will be reduced, or there will be a less demand of the steel. And second one is the economy. The cost of the production should be very minimum, so that the cost of the manufacturing will be very low. And now it is audible. Am I audible right now?
Yes, sir.
Yes.
Yes, sir.
Yeah, there is some internet issue today. I don't know. Anyways, so if you remember in the previous lecture, as I told, uh, it is economy is also important, because we have to produce steel at a very cheaper rate, and so that the final cost of the steel will be also less. And the third one is the the third point is basically the rate of production. Right? The rate of production should be also very high, right? So that we can earn more profit. So economy, rate of production, and quality, these are the three important attributes, or we can say three important um, pillars for an industry. So today's first contains the steel quality data for residuals and non-metallic inclusions. Right? So these are, first we start with non-metallic inclusions. So you can see we have two types of inclusion. One is micro inclusions. Micro inclusion means the inclusion size is very small, whereas we can have large inclusions. And basically, large inclusions are not good if they are present in the steels. But basically, if you remember, it is very difficult to get 100% inclusion free steel. Anyhow, will be have some inclusion in our steel. It may be in ppm level, but still it will be there. Right? So micro inclusions, you can see the size of the micro inclusion is 1 to 10 micron, whereas the large inclusion are that is greater than 10 micron. That is the difference. And it is also written the large inclusions are very harmful if the size is greater than 50 microns. So inclusion size, if it is greater than 50 microns, they are very harmful. If you remember, one of the major issue is during rolling process, where the inclusion may also get rolled if it is deformable, and and it will become elongated, and it will give bad surface finish, and it will give also directional characteristics or directional nature. Then you can see, can you people tell me what is the resolution of a human eye? Sorry.
So 0.2 mm.
ପୁରୀ ଖାଇଦେଲା ନିଦ ଲାଗୁଛି। ଗେଷ୍ଟ ହାଉସରେ ରହୁଛନ୍ତି କି ରିଭର ସାଇଡ୍ କଲୋନୀ ଗେଷ୍ଟ ହାଉସ? ସମ୍ବଲପୁର କେମିତି ବାଇକରେ ଆସୁଛ?
Okay, can you people tell me? I don't know. There is some network issues today I have, but can you people tell me what is the resolution of a human eye?
0.2 mm.
0.2 mm. Okay, 0.2 mm. Okay, fine. 0.2 mm or some in some literatures you can see also it is 0.1. Okay, 0.2 or 0.1 mm. Anyways, so you people am I audible?
Yes, sir.
Yes. So if the resolution of human eye is only 0.1 millimeter or 0.2 millimeter, so that means we cannot see these inclusions, right? Because their size is very small. The third point is what? This micro inclusions, if they are well distributed in the matrix, that means well distributed in the steel matrix, they can affect the grain size, they can affect the mechanical properties, right? And sometimes they can also affect the recrystallization. Sometimes this microinclusions helps in the recrystallization process. That means new strength free crystals may form due to presence of this uh, tiny particles of inclusions. And grain size, you understand, if they are well distributed, they can also prevent the grain coarsening, like L2O, L2O3 particles. They can also prevent the grain coarsening. Like L2O3 particles, they prevent the coarsening of the grains, or TiO2 particles, they prevent the coarsening of the grains. And these large inclusions are also called exogenous entrapments. They get entrapped in the liquid state during the casting process, basically. So they can come from these molds, from tundish, or from the ladles. So entrapment of the slag. This slag is nothing but an inclusion right now if they get entrapped in the liquid state. Then reoxidations of steel. Sometimes what happens during the processing of steel, the alloying element present in the steel or the iron itself get reoxidized, and that may give rise to the inclusions in the steel. And erosion of the refractory lining. During the processing of the steel, the refractory lining get eroded, and that may give rise to the inclusions in the steel. So during processing of the steel, if the refractory lining get eroded, that means if refractory lining get eroded from the any part, like from the tundish or from any part of the system, then it will give rise to the uh, this inclusions. Fine. Now you can see these micro inclusions are the product of the steel making reactions or metallurgical reactions like deoxidation of steel. So when we do deoxidation of steel, some products will come out, that is deoxidation products. They are also inclusions. They belongs to the micro inclusions basically. Uh, yeah, there is an important line here: to control the deleterious effect of sulfur, addition of manganese will be there, and the ratio of this manganese to sulfur should be greater than 0.5%. So that means when we add manganese in a large amount, it may form manganese sulfide, right? So this manganese sulfide is also an inclusion. Am I audible to everyone?
Yes, sir.
Okay, I have to wait for others to let them join. Okay, so we were in the middle of the discussion where I was talking about those inclusions, micro and large inclusions. So you understand the main cause of these micro inclusions is basically the chemical reactions happen during the steel making process. It may be primary, it may be secondary. And the large inclusions source is basically due to entrapments. Entrapments of the slag, entrapment of the reoxidation products, or due to entrapment of the refractory lining which is getting eroded from the refractories materials, right? And if you look into the composition, or you can say what are the basically these micro inclusions, they are basically oxysulfides, complex oxides, sulfides. Now quality of steel will be affected. So you can see how the quality of steel will get affected. That means if we have more sulfur in our steel, then we try to remove it. So we have to add more amount of manganese to control the sulfur level, right? So to control, so that means manganese sulfide will form and manganese sulfide will remain as inclusion, right? We could try to remove the manganese sulfides, but some manganese sulfide will be still there. So more sulfur, more sulfide inclusions. Similarly, if we have more dissolved oxygen in our steel and we try to remove it by deoxidation practice, by adding deoxidizers, so it will form deoxidation products which are basically oxides. So that means more oxygen means more oxide inclusions, right? So anyhow, we try to remove sulfur as much as we can from the steel by sulfurization technique, and by this oxygen, it is very difficult to reduce, right? Because anyhow, during the primary steel making process, we blow oxygen, and so oxygen will be obviously there in the steel. It is very difficult to remove. And there is a concept of total oxygen calculation. So total oxygen in the steel is nothing but it is the uh, addition of dissolved oxygen as well as the oxygen as oxides, right? That is the total oxygen. And measure of oxide cleanliness is the measure of total oxygen. So more is the total oxygen, more is the less is the cleanliness, right? Or just vice versa. Then it is written if total oxygen is below 30 ppm, it is okay quality steel. So basically that means there is a criteria that if the oxygen amount is below 30 ppm, then we can say it is a good quality steel or okay quality, right? So that means for a good quality of steel, we have to reduce the oxygen level below 30 ppm, right? Similarly, if we have oxygen content more than 40 ppm, it is not of good quality. It is an inferior quality steel. And you can see a figure here that the data is here that 1 kg of clean steel contains nearly 10 to the power 8 non-metallurgical inclusions. Sorry, non-metallic inclusions. So you can understand the numbers 10 to the power 8. in 1 kg of plain steel. So I told you that we cannot remove 100% inclusions, but we try to remove them as much as possible. That means anyhow some inclusions will be there. But the important point you have to remember is, if inclusions will be there in the steels, it should be in the smaller size. Micro inclusions should be there. That will give some benefit to the property of the steel. Like it can reduce the grain size, it can give you some strength, right? It prevent the grain coarsening at high temperature, or sometimes it provides some good mechanical properties like strength, hardness. Some inclusions are not harmful, but large inclusions are. Yeah, small inclusions are not harmful actually. There's another data here we have, which is talking about the residual elements. So residual elements: sulfur, phosphorus, hydrogen. You can see the sulfur should be less than 0.005, and phosphorus should be less than 0.010, and hydrogen should be less than 0.5 ppm in high grade pipeline steels. So in pipeline steels, which is used for supplying water or gases, anything, so this is the criteria. This is the amount of residuals present in the steel. And if we have deep drawn steels means, you understand, it is drawn to a large extent, maybe making wires or any sheet metals like. So here what happens, the sulfur content should be less than 0.005 and phosphorus content should be less than 0.015. Okay. And there is another few data we have here, which basically talks about different type of steels and what is the maximum value of oxygen, and what is the maximum value of nitrogen, and what is the maximum size of non metallic inclusion. Okay. So basically these are some limits. That means, as I told, we cannot remove 100% oxygen, we cannot remove 100% nitrogen, we cannot remove 100% non-metallic inclusions. That means anyhow the steel will be having some nitrogen, some amount of hydrogen, some amount of non-metallic inclusions. So if they are present in the steel anyhow, so there is certain criteria that this non-metallic inclusion side should be less than that, and the amount of nitrogen, hydrogen should be less than that. So these are the figures you can see. So if we have pipeline steels, the oxygen amount should be less than 30 ppm, and maximum amount of nitrogen should be less than 30 ppm. ppm here means parts per million. And maximum size of non-metallic inclusion is 100 micron. It should not be greater than that. Similarly, if we have deep drawn steels, then maximum amount of oxygen should be this one, 25 ppm, and nitrogen will be 30 ppm, and size of inclusion, non-metallic inclusion is 100 microns. Similarly, heavy plate, this is the figure. And for wires, yeah, so for steel wires, this is the figure. But you can see when we are producing wires, that means we need very high ductility, obviously. So that's why the size of inclusions is less, 20 micron. You can see here another fact, ball bearings. In ball bearings, basically this one is less. Maximum oxygen should be 100 ppm, and size of NMI is 15 micron, less than this one. Okay, next topic is limitation of primary steel making process. So you understand, primary steel making process means we are refining our hot metal, right? Whether we have hot metal means I'm talking about pig iron or molten impure iron, right? So when we have a hot metal, that is pig iron, that contains lot of impurities, right? Like carbon will be there, sulfur will be there, silicon will be there, manganese if it may be there, right? Silicon, phosphorus will be there, right? So we have to remove these impurities, this carbon, this silicon, this phosphorus, this manganese. If it is in the high amount, this should be removed as much as possible. So this removal of these impurities basically is taken place in the primary steel making process. Or if we have DRIs or any scrap, also we do what? We do melting basically, right? Because DRI, that is direct reduced iron or sponge iron, is a solid product, a solid iron. And scraps, if we have, we cannot discard scrap because lot of scrap generates during the steel making process or after steel making process, right? So the scrap needs to be melted and recycled, right? So these are solid products, so it needs melting also. So primary steel making process involves extensive melting of the solid raw materials, these scraps and DRIs or sponge iron, or it also involves refining operations. We have to remove the impurities present in these scraps, DRIs, or in the hot metal, right? So that is the main part of the primary steel making process. And this primary steel making process, you people know as it is carried out by blowing oxygen, by blowing oxygen basically. So when oxygen is blown, what will happen? Chemical reaction starts. What kind of chemical reactions? It is a basically preferential chemical reactions. The chemical reactions between these impurities with the oxygen, and they become oxides, and finally they will move to the slag phase because we are using also lime or basic oxides. So this so they will form a slag finally. So the thing is what? Due to this thing, what is happening? The first problem is here you can see. Yes, what okay, fine. What kind of converters or what kind of furnace we are using in the primary steel making process? These are basic oxygen furnace, which is you remember if in the undergraduate that is LD furnace, and we can use electric arc furnace EAF. We can use induction furnace. This induction furnace is for melting basically. Electric arc furnace by generating arc we are melting and refining, and basic oxygen furnace you understand the lining is basic lining, and we are blowing oxygen, right? So what is the problem here in the primary steel making process? The problem is the slag reach in FeO. So slag will reach in FeO, iron oxide, due to oxygen blowing, because we are blowing oxygen. So it doesn't mean that only the impurities will get oxidized. Some amount of iron will get oxidized. It will form FeO, and FeO is an oxide, so it will move to the slag phase. So slag will be reaching FeO during the steel making process. And sometimes we also intentionally add iron oxides so that it will form slag rich in FeO, right? So this is one of the major issue. So can you people tell me? Okay, fine. I will ask later. Next one is the liquid steel forms is rich in dissolved oxygen. So you can see the amount of dissolved oxygen in the steel. It is 500 to 700 ppm. Then it is very high level in the steels. So that means since we are blowing oxygen, the amount of carbon is getting reduced. But the problem is what? The steel will contain dissolved oxygen. So these are the main major issue. One is high amount of FeO in the steel slag, and high amount of dissolved oxygen in the steel which is produced. So now what is the consequence of this? The consequence of this is desulfurization will not take place. So we understand that means for desulfurization we need some reducing atmosphere basically in the furnace, right? And or in other words I can say we need a slag of reducing nature or less oxidizing nature of slag. So can you people tell me what is the meaning of oxidizing slag and what is the meaning of reducing slag? Or what decide the slag will be reducing one or it is oxidizing one? Basically, you understand if your slag will contain more weight percentage of FeO. FeO is an oxidizing material, right? Because it supplies oxygen, right? So if the weight percentage of FeO in the slag is more, it is an oxidizing slag. So that's why it is called slag is having high oxidation potential, or slag is having a high oxidizing power of slag. So oxidizing power of slag is determined by weight percentage of FeO. So more weight percentage of FeO means it is oxidizing slag. So similarly, just opposite, if the FeO weight percentage is less in the slag, it is reducing slag. It also contains some amount of carbon, obviously. Right. So basically, to do desulfurization, we need a slag of or reducing nature slag or a slag with low FeO content. Right. So that means you understand the consequence of this primary steel making process is high amount of FeO in the slag and high amount of dissolved oxygen. So this condition is not favorable for removal of sulfur. So desulfurization will not take place. So this is one part. And the part is what recovery of alloying element will be very poor due to this dissolved oxygen. And this is due to oxidation of alloying element and they goes into the slag as oxides. So that means during primary steel making process, we cannot do desulfurization. You understand what is the thing. And second one is we cannot recover lot of alloying elements if we have, right, during the primary steel making process. The recovery will be poor, obviously, because oxidizing atmosphere is prevailing, and so the element will get oxidized, they will move to the slag phase. So recovery of alloying element is very poor due to this oxidizing nature. Then there is another problem, erratic nature of alloy recovery in different heats. So you understand the heat. So in different heat, the recovery of alloying element will be different. So it is obviously another issue because customer never want that you supply the metal or supply the steel with different weight percentage of alloying element. It should be a constant. Erratic means it is variable, basically. Then another issue is poor cleanliness of the steel obtained after primary steel making process. Poor cleanliness of steel, you understand that means it is not clean in terms of oxygen, in terms of sulfur, right? Or in terms of any inclusions also. Now that is the need, that is why there is secondary refining or secondary steel making process. So secondary steel making process come into picture due to these things. So you can see secondary refining is basically done in ladles or ladle furnace after tapping the liquid steel from the furnace. So basically secondary refining or secondary steel making process are carried out in the ladles, or in the, there is certain furnace called ladle refining furnace also, LRF. Ladle refining furnace, LRF, yes. So what is the objective of secondary refining? So these are the three objectives: to get right chemistry of steel, because you understand even after primary steel making process we have lot of impurities or we have certain issues in the chemistry. So to get a right chemistry of steel, we need to do secondary refining, right? And then able to get a homogeneous composition. So composition may not be homogeneous after primary steel making process. So we need to get a homogeneous composition. Then the cleanliness can be improved during this secondary steel making process. So these are the three things: right chemistry, homogeneous composition, and clean steel. Now, how to fulfill the objective of secondary refining? So these are the different processes carried out during secondary refining process or secondary steel making process. One is deoxidation practice. So deoxidation practice means you understand after the end of the primary steel making process, the steel will have lot of dissolved oxygen, like above 500 ppm, right? So you need to remove that dissolved oxygen. So that can be removed by deoxidation practice. So in the deoxidation practice, basically we add deoxidizers, or we add the alloying elements which have high affinity towards the oxygen. Like you can add aluminum, you can add titanium, vanadium, silicon, carbon, right? We can add those elements. Second one is to remove dissolved oxygen. Then carburization, decarburization. Suppose during the primary steel making process, the carbon goes to a very low level, but the customer demand is it needs a particular carbon level. So what we can do? Carburization. That means we will intentionally add carbon into the steels to improve the amount of carbon weight percentage. Fine. And decarburization. Suppose after the end of the steel making process, we cannot remove the carbon sufficiently, or we want a steel of very low carbon, right? Very low carbon. So in that condition, we have to go for decarburization. That means decarburization means we can remove the carbon further during the secondary refining process. The desulfurization. Basically, as I told, desulfurization is never carried out. Basically, in the industry, it is not carried out after primary steel making process. We try to remove the sulfur before primary steel making process. That is called external desulfurization of hot metal, right? So it is external desulfurization of hot metal is a process which is in between the iron making and primary steel making process, right? And I told you the reason behind that in the previous lecture. But even if sometimes what happens, if sulfur is not getting removed, we can remove the sulfur externally in the ladle after primary steel making process by creating suitable atmosphere, reducing atmosphere. Then degassing of nitrogen and hydrogen. Okay, fine. So you understand we have to remove lot of nitrogen and hydrogen if it is there, right? Then inclusion, degassing means removal of dissolved gases, nitrogen and hydrogen basically. Inclusion modification, yeah, this is very important. You can see we have micro inclusions, macro inclusions, or big size inclusions. If they cannot be removed properly, we can do one thing, we can modify them. That is called inclusion engineering actually. We can modify their shape, like if they are elongated or if they are something different shape, we can modify them into spherical shape, right? Or we can modify their chemistry. You can modify their chemistry so that they will become liquid in the steel and they can be removed easily. So these are the inclusion modifications. Then control of liquid steel temperature before casting. So this is also important because after secondary steel making process, we need to do casting of it, continuous casting or ingot casting or batch casting. So there is a particular pouring temperature is there. So steel will be taken to that temperature, or that is called superheat temperature also. Steel will be in the temperature to a high temperature. Above that, the melting point, basically, or liquidus temperature. Right? So if pouring temperature is improper, then quality of the cast will be degraded. We will have a poor quality of cast product. It should not be very high, it should not be less. Then what are secondary refining process in modern steel making practice? So these I have noted I think I have noted all the secondary refining processes in modern steel making practice. One is the LF, ladle metallurgy. As I told, LRF, ladle refining furnace. So we can do a lot of things in the ladle. So that is called ladle metallurgy, basically. We can add alloying elements to meet the chemistry. We can do many things in the ladles, right? We can remove inclusions also in the ladles. Many things can be done. Then IGP. IGP is inert gas purging. It is inert gas purging, actually. Inert gas purging. Inert gas means basically we are Purging means we are blowing inert gases like argon into the molten steel after primary steel making process. This is basically to homogenize the steel. Homogenization in terms of temperature as well as the composition. Suppose we have added some alloying elements and we want the alloying elements should be uniformly distributed throughout the steel. So we can purge inert gases from the bottom of the ladle or from the top. Basically, there is a facility to purge the inert gas from the bottom of the ladle, so that inert gas will bring agitation in the steel and it will bring homogenization in terms of temperature and composition, right? Then VD, there is vacuum degassing actually. Vacuum degassing. So that means vacuum degassing. This process is called vacuum degassing. Means we will degas, we will remove the dissolved gases like nitrogen and hydrogen from the liquid steel in the second steel making process by applying vacuum, right? Because you understand, the moment we are applying vacuum, the partial pressure of the dissolved gases will be reduced, right? So you understand, if the partial pressure will be reduced, then what will happen? It will automatically come out from the steel. So during vacuum degassing, we can also do some purging also, so that we can do recirculation inside the ladle. The steel can be recirculated, right? So can you people tell me what is the relationship between the partial pressure of do you people know about this Sievert's law? Anybody remember Sievert's law? How many of you remember Sievert's law?
So it's predict the solubility of gases and metals.
Yeah, it tells about the solubility of gases in the metal. So what is the what is the relationship? Okay, what is that formula, or what is the relation? Or how you can justify the solubility of a gas in the liquid steel by this law? Basically, solubility of a gas in the molten metal increases with increasing in the partial pressure, right? So if suppose I'm talking about partial pressure of nitrogen, if nitrogen partial pressure will be increased, then solubility of nitrogen in the steel will increase. I'm talking about the liquid steel basically, right? So similarly, Sievert's law is telling that solubility of a gas in the liquid steel or in molten metal is directly proportional to root over of partial pressure basically. Anyways, so you understand, that means if you want to remove the dissolved gases, you have to decrease the partial pressure of the gas. So that can be done by using vacuum, because vacuum means negative pressure. We have to create a negative pressure in the molten steel so that the partial pressure will reduce and it will come out. Anyways, then VAD is nothing but, this is vacuum degassing process. Vacuum arc degassing. So that means here in the ladle we have a facility to generate arc. Arc means arcing. That means by using electrodes we can generate arc so that the temperature will rise. So because you understand, during the subsequent operation, many operations, the temperature of the steel will reduce, right? That should not be get reduced, right? Because further it has to be cast. So to maintain a temperature or to rise the temperature of the steel, arcing is essential, right? So this will facilitated by VAD, vacuum. So there is a facility of vacuum and there is a facility of arcing, and we can do degassing also. Then VOD. So vacuum oxygen decarbonization. Sometimes, as I told, if you need, suppose you need steel which will contain very less amount of carbon, so you can remove the carbon as much as possible by using oxygen and vacuum, right? Because you understand, we have to blow oxygen will react with carbon to form carbon monoxide, and if we apply vacuum, this carbon monoxide can be also easily removed. Then RH, this is a degasser actually, RH degasser. This is a technique of degassing of steel, RH degasser, to remove the dissolved gases. Then IM is, it is injection metallurgy actually. Injection metallurgy. Injection metallurgy means we are injecting something into the molten steel. Basically, injection metallurgy is carried out for inclusion modification, to change the shape of the inclusion or to change the melting point of the inclusions, right? So these are added. So if you have heard about calcium injection, calcium wire injection, right? That is, we are injecting calcium wires, right, into the steel, molten steel, so that it can modify the inclusion. That is Ca and Ca. Ca means calcium and iron injection, and Ca is the calcium silicide. Basically, this calcium will go into the steel and it will form a coating around the inclusions, like for around the Al2O3, for example, right? Because you understand, Al2O3 is an inclusion, it is an oxide, right? So it has very high melting point, above like 2100 or 2200 degrees centigrade. So steel making temperature is 1600 to 1700 maximum. So that means this Al2O3 will remain as solid particles. So if we add calcium, it will form a coating and this will this calcium will remain in molten state, so it can be removed easily. Because this calcium will form a coating and it will float to the surface. So we can remove the inclusions of Al2O3 easily by forming a coating of calcium around the Al2O3 particles. So we can change the shape and we can change the chemistry. By this we can also change the melting point by changing the chemistry also, to make them liquid in the working condition. Okay, I'll stop here. I will continue my lecture from the next class.